Buoyancy, or mass, volume, and density. Archimedes' principle is that an object immersed in a fluid will experience an upward force equal to the weight of fluid displaced. In other words, if we take an object, immerse it in a fluid like water or oil or even air, uh, for instance, we exist here at the bottom of an ocean of air, and so we can see buoyant forces causing hot air balloons to float. Okay. So in this particular case, the object, this idealized cylinder, has a mass and therefore weight. But because it's immersed in this fluid, it also has a buoyant force. Now, how do we understand that? First of all, we'll start with mass and volume. Mass is one of your base units. Volume is a derived unit, derived from length. A volume is equal to a length cubed. Now, we can measure volume in meters cubed. In this particular lab, the PHET Colorado simulation, they're going to measure volume in liters. But it's the same thing. Density is going to be used, we're going to use the Greek letter rho to represent density, and it's simply the ratio of the mass to the volume. The gravitational force acting on the object, any object with mass, is simply going to be weight is going to equal mass times gravity. Now, this is true anywhere near the surface of the Earth, of course. We know there's a more complicated expression for the gravitational acceleration further away from the surface of the Earth. Pressure, or force per unit area, is simply due to the weight of the fluid above any given point and is going to be exerted on the outer surfaces of our object. I'm going to state without proof that the pressure on either side at any given depth around the sides of the cylinder are going to balance each other out. However, the force exerted due to pressure at the top of the cylinder and the bottom of the cylinder will differ because the pressure at the top and the pressure at the bottom differ. You only have to have taken a swim in the deep end of a swimming pool in order to have figured that out. So the buoyant force is going to be equal to the difference in pressure between the top and the bottom of the object times the area on which that pressure is exerted. Now the pressure there is simply going to be the mass per unit volume, or the density, times the gravitational acceleration times the depth in the water. Notice that this is going to have units of force per unit area, or pressure. Again, once we incorporate that into our buoyant force, we have the difference in force between the top and the bottom of the cylinder is going to be equal to the difference in the depth of the top and bottom surfaces times the density of the fluid times the gravitational constant times the area. Again, Archimedes' principle. An object immersed in a fluid will experience an upward force equal to the weight of fluid displaced. In this particular case, we have a diver, and through some combination of voids and weight belts and his own body mass, he's managed to achieve a state of neutral buoyancy in which his density is equal to that of the water. Average density is equal to that of the water. We can also have positive buoyancy. Here, the density of the water is greater than the average density of the object. Notice I said average density because one of the floating objects that we're the most interested in are seagoing ships. Now, obviously, iron used to make most ships, steel actually, largely composed of iron, is denser than water. But its average density of a ship, and so the iron hull plus all of the air voids and such inside the ship, is less than that of water. Now, if we were to imagine this object completely immersed in the fluid, we would see that the weight of fluid displaced, the weight of the water displaced, would be greater than the weight of the object itself. And so the buoyant force would be greater than the gravitational force, and the object would pop to the surface. You could see that, for instance, if you take an air balloon, go swimming with an air balloon and hold it underwater, it'll simply pop to the surface. The volume displaced is smaller than the volume of the object. And it'll only be partially submerged once the buoyant force and the gravitational force come into equilibrium. Once the object comes to the surface, it's no longer displacing as much volume of fluid as it did before, and so the buoyant force begins to become less in magnitude, until the gravitational force and the buoyant force are equal to each other, and the object is in equilibrium. Again, neutral buoyancy. The buoyant force is equal to the gravitational force. The net force is 0, and the density of the water is equal to the average density of the diver. We can also have negative buoyancy. The buoyant force is less than the gravitational force. When you work with the simulation, one of the materials you can work with is brick. The density of the water is less than the density of the object. That doesn't mean that there's no effect here. We have the apparent weight. The apparent weight is the difference between the weight as it is measured in the fluid inside and outside of the fluid. For instance, you can see off to one side there's a scale out of the fluid and a scale in the fluid. The apparent weight then in the fluid is going to be mass times gravity, which is just your regular expression for the weight, minus the buoyant force, which is density times the acceleration due to gravity times the volume. If you'd like to know more, I would refer you to Herbert Goldstein's Classical Mechanics by Addison Wesley, 3rd edition, June 25th, 2001.